A simple tap of a screwdriver across the terminals is not a safe or effective method for discharging capacitors. This can result in a sudden release of a large amount of energy, potentially causing injury or damage to equipment. The proper method for discharging capacitors is to connect a resistor across the terminals. The resistor provides a gradual path for the energy to dissipate, reducing the current flow and voltage drop. The value of the resistor depends on the capacitance and voltage of the capacitor. A common rule of thumb is to use a resistor with a value of around 1000 ohms per volt of capacitive voltage. For example, a 400 volts capacitor would use a 400,000 ohms resistor. The energy stored in a capacitor is given by the equation energy equals 1/2 times capacitance times voltage squared, where energy is the energy in joules, capacitance is the capacitance in farads, and voltage is the voltage across the capacitor in volts. For a 400 volts, 390 microfarads capacitor, the stored energy is energy equals 1/2 times 390 microfarads times 400 volts squared equals 31.2 millijoules. The current and power available from the discharge of a capacitor depend on the circuit connected to it. By manipulating Ohm's law, we can calculate the peak discharge current and power. Peak current equals voltage divided by resistance. Peak power equals voltage squared divided by resistance, where peak current is the peak discharge current in amperes, peak power is the peak discharge power in watts, and resistance is the resistance in ohms. For example, if the capacitor is discharged through a 400,000 ohms resistor, peak current equals 400 volts divided by 400,000 ohms, which equals 1 milliamp. Peak power equals 400 volts squared divided by 400,000 ohms, which equals 4 milliwatts. While capacitors primarily pass alternating current signals and block direct current, they are still widely used in direct current systems for various purposes. Firstly, smoothing. Capacitors can be connected in parallel with a direct current power supply to smooth out voltage fluctuations and reduce ripple. Secondly, energy storage. Capacitors can store energy and release it as needed, making them useful in applications such as switching power supplies and uninterruptible power supply systems. Thirdly, filtering. Capacitors can be used as filters to remove specific frequency components from a direct current signal. Fourthly, coupling. Capacitors can be used to connect two direct current circuits while isolating them from each other. Finally, blocking. Capacitors can block direct current while allowing alternating currents to pass, enabling signal separation in circuits.